Okay, folks, good afternoon. And is everything okay? Can you hear me fine? And do you see the image of that? Good. Thank you, Kelly. Thank you. All right, let's get started. Uh, we are on chapter 21. First of all, do you have any questions? No questions? All right. If you don't have any questions, let's just work on chapter 21. We are almost about. And what was the class average on the exam? I think the class average was 73 or 4. I mean, we had some students probably drop the course, but they're still on the roster, so they get 0. They bring the average down. I think it was around 73, 74, or 75. I don't remember exactly, but in that range. It was around between C and C plus. Your first midterm was about between A minus and A. The average was between A minus and A. This was between C to C plus. You guys did better than my previous classes for the second midterm. I think it was because of my warning. I wanted to warn you in advance, and I'm going to do the same thing, that your final exam is going to be a little bit more challenging than, in a way, it's challenging. In a way, it's easier. It's when I say it's challenging because you're going to see more formulas, you might get confused to see which formula you have to use. And another way of saying it is easier because you're going to see that we are almost using the same thing since chapter 16, and it's just a confidence interval and null hypothesis, but it's in different formats. In one case, you don't have sigmas unknown. In one case, you're estimating the mu population mu average, or in another case, you are doing 2 samples instead of 1 sample. I mean, we are doing exactly the same after, I think, chapter 16. It's inference statistics. So you do 2 things. One is confidence interval, and the other one is null hypothesis and alternative hypothesis, tests of significance, so-called. So it depends how you look at it. You can say that, well, it's easy because we are repeating the same thing with a little bit differences. Or you can look at the formulas because you're dealing with several formulas. You got to recognize which formula is used for what. So I think what I'm gonna do, I'm hoping that I can finish this is going to definitely 21, chapter 21 is going to be finished today. And I'm hoping I will get almost to the end of chapter 22. And hopefully we will finish chapter 22 and 23 next week, I'm hoping. And then we are done with the chapters. And the last week, which is going to be week 10, I'm planning to go through some problems, from chapter 16 or 17 all the way through chapter 23. Maybe for those 2 days, go through some end of chapters problems. And I know that helps a lot because we can see the differences and do different things. But I'm hoping I can finish, even if I finish it on, halfway through this on last Monday. That will give us a lot of time to at least do maybe 10 problems. We'll see. Let's play it by ear. Hopefully we'll get there. Okay. Any other questions? No other questions? You're okay with the Excel and web work and everything else? And all right, sounds great. Okay, we did this problem. This was the problem we were working on it. Remember, example 5. In this example, we had 2 groups of students. If you recall that one was coached, the other one was uncoached, so to speak. They had different number of students. They dealt with it, different values for means and different values for means. We had this, you had this before. Different means, different standard deviation. The only difference between these, you have part A and part B is, in part A, we looked at the two groups when they did the first try. Each group did the first try. That means we looked at the tests of significance. We concluded that what the t-value and so forth and so on was. Is that the correct? Yeah, uncoached. Okay, it says if the, okay, we did this. Did we finish this? I think we have this something, we calculated t, didn't we calculate t-value there? No, we haven't calculated this, so I'm sorry. We gotta finish this. I thought we finished this. Okay, we are here. Okay, so this is for the first try. If you recall that, this is the coached information for group 1, uncoached for group 2. Okay, we are comparing those two groups, and basically we want to know here, is there a significant difference in the scores between coached and uncoached students? Okay, we know that the normal hypothesis is going to say the difference is 0. That's what the norm is. We don't see the difference. And the alternative, because it says a difference, so we have to say not equal to 0. Or we can rewrite this one as mu1 is equal to mu2, or mu1 is not equal to mu2. Just take this one to the other side, change the sign in both cases. You have that. Right off the bat, the question is this a two-sample or matched pairs test? It's not a matched pairs test because the number here is for the group 1, 427, for group 2 is 2,733. So they don't have the same numbers. Right there, we can say it's not matched. So therefore, it will be a two-sample test. And then we calculated t. T is based on t statistic. We calculate this, you know, you look at the formula. We had this formula before, right? And what did we have this formula? We had this formula somewhere. Let me see if I can find it here. This is the formula we are using on page 2. So that is the formula, x bar, and because mu1 minus mu2, because we're looking at the difference, that is 0. We put 0 there. And this is standard deviation for the first group and sample size for the first group and so forth and so on. We put all these values there, and we ended up getting t equal to minus 1.236. And you know how to get this value. Okay, so based from this value, we're going to get the p-values, basically. So what we have here, since if you look at the table, this table doesn't have any negative numbers. So instead of calculating this part of the whole thing, we're going to look at this part, which is the positive part. So that is the reason we say we are going to make the t positive and then go look at the p-values there. It's going to give you the same answer. Because Tn minus T or T star minus T star, they are the same. The only difference is the sign. Okay. So we can look at this. Let's see. What do we have? First of all, you know the degrees of freedom. What is the degrees of freedom? We calculated that. Between two sample sizes, we pick the smaller one, which is 427. And we subtract 1 from that, that becomes the degrees of freedom for this two-test sample. So we have the degrees of freedom here. So now we look at it here. In this case, remember, if you look at this column here, you don't see 427. What is the closest number for 427? Either you have to pick 1,000 or 100. But we learned that even if you have 999, you pick 100. You pick one below that, not one above that. So 426 is here. Below that would be 100. So my degrees of freedom here on the table, it's going to be 100. But if you're using Excel, in Excel 426, you can put 426. Here you can't because we don't have, I mean, if you go look at complicated tables, you might see 426 there, but not in this smaller table. So we're going to treat it as 100. So that's going to be my row, 100. And now we are looking at what is the number, what is the value of t? We said that t is 1.236. So where does 1.236 lie? 1.236 lies between 1.236. So it should be between these two numbers, right? It should be between 1.042 and 1.290, right? Everyone agrees? Good. So what we are going to do now, we're going to rotate this. That is the number I have. So if I draw a line all the way down here, since this is like if mu1 is not equal to mu2, the difference, so we got to look at two-sided value, which is going to be this one. And when you look at this two-sided value, then the p is going to be between these two numbers, between 30% and 20%, for 0.3 and 0.2. Okay, are we okay with this? So therefore, we are going to rewrite this one. So since t lies between 1.290 and 1.042, that is the value of 2. And if you drop it down, all the way down, and you see here two-sided, and as I said, two-sided because you have here, it's not equal sign. It's not, it's a difference. We're looking at the difference. So two-sided side, and we saw that this is going to be 0.30, 0.20. So the conclusion would be 30%, and that means p-value lies between 30% and 20%. That's high. So basically, what does this tell us? It tells us that we failed to reject the null hypothesis, which is H0. So if you fail to reject that one, from here, you fail to reject it, that means you accept it. You accept the null hypothesis. You accept, no, only if it is above 1,000, always choose below. He said, even if it is 999, exactly. If it's 999, to choose 100, yes. If it is 1001, you choose 1000, exactly. Always you choose the same line or below that line. If your number matches with the same row number, then you pick that one. If it doesn't match, you pick one below that, or one, whatever the below that number is. Anyhow, so we have, can you move it down? Okay. All right, 20% p-value is between 30% and 20% based on what we have here. So we wrote that, we said fail to reject the null hypothesis. So from here, if you fail it, that means you're accepting the null hypothesis. What is a null hypothesis? Null hypothesis is telling you that mu1 minus mu2 is equal to 0. From here, you say mu1 is equal to mu2. So that means there is no difference. There is no difference. There is no difference between these two groups, between these two groups. These two groups in the test. Okay. If this was between 3% and 2%, that would have been a different story because it's less than 5% in both cases. And you could just say that we reject the null hypothesis. That means there is a difference. Instead of writing this, you have to say to cross this equal sign and say mu1 is not equal to mu2, so forth and so on. All right? Okay. If you don't have any question, we're going to move on to the next page. Next page is, now it says, is there a significant difference in SAT scores between first and second tries when students are coached? So you're picking one sample rather than picking coached and uncoached. You're going to pick one coached and you're going to look at the 2 tries on them, first try and second try. So based on that, this is a 2 sample or a matched pair test? What do you guys think? It's obvious, right? So it is a matched pair. Exactly, you're using the same number of students, but the only difference is you're doing 2 tests. What if one of our values greater than the significance between our second p-value is not? I don't understand the question. Can you give me some numbers? I don't. What if one of our values is greater than the significance, but our second p-value is not? But I don't understand what you're saying. Can you elaborate on that? Can you give me some numbers so I can understand? Maybe someone else can understand it. Can you paraphrase it or something? Okay. You can have a value to be, if you have a limit of numbers, if you have 2 numbers, your number is going to lie between these 2. So you might, I think that what you're trying to say that if this is like, say, I'm guessing, this is my guess, I'm guessing, let me find a piece of paper. I'm guessing what you're saying is like a p value. What if p value is statistically significant, but the other, what is the other? Don't understand the other. P-value lies between 2 numbers, right? I think that what you're saying that if this is like a less than 0.5 and this is like a 0.6, is that what you're trying to say? The range that it falls. Okay, good. Okay, so if you're looking at this number, no, this should be actually 6 here, 5 here. Or maybe I can put something like this, make it even better, 4, 5, and this would be, what do you want to have, 5.5? So 5 is our limit. What if we have something like this? That's what I'm guessing that your question is. Okay, if the p-value is like this, you got to make a judgment call. So you can say that this p-value might lie towards this 0.45, or it might be above 5. In either way you make the decision, it is up to you how you're going to justify to make this decision. When I give you questions, you can draw the conclusion clearly, like the way we did it here. But if you're doing testing on your own, say you're doing some research, you gather some data, that depends on your experiments, what you're doing and how you can answer this question. You might tighten your range, say that even 0.4 is above the threshold for you. Therefore, you can fail to reject that. You go back to your experiment, whatever the experiment is doing, you have to make a conclusion. Do I move towards 0.45 or do I move towards something greater than 5? If your threshold is greater than 5, then you say it's okay. If you're moving towards this, then you say it's not okay. But for the sake of, that's a good question actually, but for the sake of what we are going to do and what you're going to see in the final exam, it's going to be clear the way that you see it here. It's not going to give you something kind of dubious, say, oh God, in one case, one side is saying this and the other side is saying. If you see something like this, I might give you the threshold is 6%. So definitely this, any number you pick here is less than 6%. So I will fix that problem for you. Okay? Good question. Okay, let's go back to here. What was the threshold on the last block? We assume that the threshold is 5%. Remember from the get-go of it, when we started this, we said that if it's not given to us, if alpha is given it to us, then we look at, always we look at the p-value. Eventually we have to compare that p-value with the threshold alpha given to us. If alpha is not given to us, the assumption is 5% is good. Okay? So in this case, when we say 5% is good, so this lies between 20% and 30%. It's way, way above 5%, and therefore that's the reason we fail to accept it. Because the assumption is 5% is good. Anything below 5% is acceptable. And again, when you're doing your experiment, in some experiment, even 2% might be too much. It depends on what you're doing, what kind of experiment, and what kind of threshold you want to put in your experiment, and analysis, and so forth and so on. But for our all practical purposes that we are doing here, the assumption is 5%. If it's less than or equal to 5%, then we say we can fail, we can reject the null hypothesis. If it's greater than that, we say we fail to reject the null hypothesis. If I don't mention it, and you calculate the p-value, if there is an alpha there, you got to compare it to that alpha. If alpha is 10%, if it's less than 10%, then you say you reject the null hypothesis. If it's not, then you say you fail to reject the null hypothesis. Are we clear on that? That's an important question. Good, good. All right. Let's move on. Is there a significant difference in SAT score between first and second tries when students are coached? Is this a two sample or a matched pairs test? It's a matched, because you're doing two tries on the same number of students, and you have a plan for what you're doing, basically. So basically, each student, so it is matched, and you can say each student tests twice. Okay. So let's write the values for this. Remember, this was for coach. I'm going to write this one here because we're going to use these values again. So we have, this is coached. P1. So here, X bar 1 is equal to 500. S1, I'm going to put Greek 1 here because I'm going to use the other one too. S1 is equal to 92, and N1 is 427. Right? This is for the first try. For the second try, we have values. What are those values? For the second try, the second try. So for the second try, what do we have? X bar is, let's look at it. For the second try, the coach group received 529 S97. So X bar 2 is 529. S2 is, what did I say, 97. And N2 is the same as before, 427. So that's for the second try. So I just want to mention something here. Coached group. Here we used first basically Greek one stands for first try, and two stands for second try. Just clarification of the note, symbols, notes. All right. So what do we want to do? Again, we have to write the null hypothesis and also alternative hypothesis. So what is the null hypothesis? Null hypothesis tells me that there is no difference between first try and second try, right? So the null hypothesis, H not H sub 0, tells me that mu1 minus mu2 is 0, or mu1 is equal to mu2. Okay? Alternative hypothesis is asking us to do the experiment. Is there a difference? So that means mu1 minus mu2 is not equal to 0. Is there a difference between two tries, first try and second try? Okay. So what do we need to do? We gotta find a t statistic, right? T is equal to, we're gonna use that formula again, x bar 2 minus x bar 1, and this is minus 0 for this one, divided by square root of, you have S2 squared over, your N2 is the same as N1. So I'm going to write 427 for both of them, because both of them are 427, plus S1 squared 427. So plug the numbers here. So we have 529 minus, this is x2, x bar 2, x bar 1 is 500, divided by square root of S2 is 97 squared divided by 427, plus S1 is 92 squared divided by 427. Okay, just a calculation, arithmetic. So the difference will be 29 divided by, I've done this. This has a common denominator. You can do this, and this squared plus that squared, and then you get 59 here, and you still have square root of 427. This would be 29 times square root of 427 divided by 59. And if you do the calc, put it in your calculator, you're going to see what you get. You get 10.157. I thought, let me see. I thought that we cannot use this two sample test because this is a matched pair design and the groups are not two independent samples. Wouldn't we use a regular test? But regular test we're using for two samples. It is, when you look at here, we are looking at the difference in regular, whatever you call it, regular test, whatever you, because we don't have, we're using t-test here because sigma of the population we don't know, and we are calculating, we went through this definition, whether, yeah, you go back, is it on chapter 1? Or chapter 1, let me just see if I can find it. Here what is this the one? Yeah. See that? Here we are using for interval of this, we are using this formula. for the H for the confidence interval, and where is my other? And here we are using the test statistics T for this one, right? This is for two samples you're using. If it's paired versus not paired, that is the only difference we are using. Are we okay with that or no? The tries are independent of each other. Requirement C of the first page, requirement of C first page, requirement of samples are independent, different individuals, and no consistent, reasonable way of pairing individuals between samples. So yes, when you look at the samples, the first sample, first try is different than the second try, right? They are independent of each other. We are doing that. And you're pairing them. If you can pair them, reasonable way of pairing them, you can do that too. You can use it. Does it make sense or no? No? Yes? Maybe I can find another example last week, we can work on this one a little bit more to show you paired versus non-paired, right? Two samples, but you're using the same formula for both of them. The tries that we did, it makes sense that the two tests are independent of each other. Yes, yes, they are. As long as it's not, we are not doing the same thing. So you pick one set of students and then you pick another set of students. You're doing totally independent of each other. And that's the reason you can see the values are different, right? You can see this sample that you took versus that one is different. But the only thing is the same is the number of students the same. I will come up with some, find some examples that will work on this, the difference you can see between pairs and in both cases, two sample and also matched pairs. That would be on last week. But if you got the idea that they are independent of tries, then we are okay with that. If you didn't, then we'll do more examples later. Okay, so we are here. T is equal to 10.157. So this is T. Now, if you look at this T value, how do we find this? Again, we have degrees of freedom is 427 minus 1, right? That would be 426. So again, we are going to go look at here, 426, and 426 is going to be against 100, right? So when it's 100, now you're looking for a number here is what? It should be 10.15. The largest number you can see here, it's 3.390. It is way off the chart. You have to go all the way to the right, right? I mean, this is like a 1/3 of what I have here, basically. 10.1. So that means you have to have maybe 20 more columns to get to this number, to the right of this. So when you look at the last number, because it's no difference, maybe you're looking at the difference, the p-value is going to be the two-sided value. That means p-value must be less than, way less than 0.001, because your number is way out there, so it's going to be way smaller than 0.001. So therefore, for all practical purposes, we can say p-value, it is way smaller than that value. And that is nothing but saying that this is like a 0.1%. It is much smaller than our 5% threshold that we have. So from here, we say we reject null hypothesis H0, and if you reject the null hypothesis, H0. So therefore, based on what we have, we say there is strong evidence of a significant difference in scores between first and second prize of coached group. Coach group, coach students, or that means mu1 is not equal to mu2. Okay. Questions? Okay, we had several good questions. Okay, if you don't have any questions, then we are done with chapter 21. Then we can move on to chapter 22. All right, chapter 22. All right, in this chapter, now, this is an inference about population proportion. Remember, this is a population. Previously, we had a mean proportion. Now we have a population proportion. No, we had a, we had a population mean. Now we have, before we had a population mean, then we have population proportion. And chapter 23 is going to deal with two proportion. Remember, we had two population means, we had one population mean, two population means. Now we have population proportion 1, and then we are going to have 2 of those. Now with chapter 23. You see the similarity that we are going through? So instead of using mean as our main goal to estimate mu, we are going to estimate the population now. We used, if you here on chapter 1, basically we used 2 samples, the difference in 2 samples, estimated mu1 minus mu2, because this was comparing 2 means. This is chapter 21, and chapter 20 was 1 mean. So this is chapter 22. We are doing it with 2 proportions, not means, 2 population proportions. I mean, 1 population proportion for 22, and chapter 23 would be 2 population proportions. Okay. So let's just suppose that a researcher is interested in, I don't know, estimation of a population proportion. This is basically, this is a parameter. Again, it's a population. We are dealing with population. And we will label this one as like a P, population proportion parameter. I will draw a table and make it more clear. But like example of this could be like you're looking at the proportion of all US adults who approve of the Congress's performance. Or it could be a proportion of all people in US who, I don't know, prefer Coke over Pepsi or Pepsi. Or you can say population of adults who prefer action movies over other movies. It's just you're looking at the proportion of something in the population. That is all. And we are going to estimate that. And so in this case, you're going to deal with basically number of successes and number of failures. And basically, we are going to look at yes versus no. That means you're looking at successes versus failures. And you're going to see that we are going to use sample proportion with P, population proportion with P. This is P caret. You know, you put a caret there or hat. That would be for sample. And then we use P for population proportion. This is like a same thing we did with just a sample mean. In sample mean, instead of using P caret, we used X bar. Instead of using P, we used mu there. It's a counterpart of that. We're having it here. So this chapter is going to cover, again, confidence intervals and significant tests for a population proportion, not for a population mean, for a population proportion. That is the important part. The last two chapters deal with proportion, population proportion. In a broader sense, basically, I don't know, the concept we cover here, it's greatly the same as those we covered earlier. Again, we are dealing with confidence interval tests of significance. And again, you're going to calculate the p-value. You have to look for t statistic and z statistic in this case, calculate that from there, find the p-value, and so forth and so on. The same thing that we did before. Again, so far our discussion, what we had so far, the discussion up to now, based on the means, population means. Now we are switching gears and we are moving towards another parameter, population parameter. We call that proportion. Okay. Let's go through the definitions and do a few examples. It becomes more clear. Okay. Definition. Instead of asking what the mean value of some population characteristic is, we ask what proportion of the population satisfies some conditions. And again, when we talk about the proportion of population, we are going to represent this with P. If this was a mean here, that would have been mu, but this is P. Example is 38% of a large lecture psychology class reports that they regularly attend class, 38%, versus the mean attendance rate of a large psychology class is 1.4 lectures per week. So now if we define that, if we look at this one and in terms of the sample, first of all, the sample should be SRS, always through the whole book, we want SRS. Size of the sample is N. P is the population parameter, P, we set it here, P, actual population parameter of successes. I should mention successes, yes. And the sample proportion, we use P caret, you know, with a caret under our hat, and this would be basically sample proportion. Sample proportion. And we look at it, if you look at sample proportion, you look at the desired number of successes, or we call it desired number of successes in sample. divided by total number or sample size, n. And that gives you this p. It's the same as when we dealt with the x bar. Remember, x bar was you took all the data values and divided by n. It's similar to that. There we found the x bar mean. Here we are looking at the population of the sample. That was the x bar. Okay, sample proportion is comparing here. Sample proportion, which is p hat, is to population proportion, which is p, as sample mean, which is x bar, to the population mean, which is mu. So we have this. So if I want to put in a table, it makes better sense if I draw a table, make it in a way clear. So we have this table. Here I'm going to put mean, and here it's going to proportion. Proportion. Here I'm going to put sample. Another name for sample is statistic. And then it's going to be population, represented by parameter. So mean of sample, that would be x bar. Mean of population, that would be mu. Proportion of sample, that would be p hat. Proportion of population, that would be p. You see that? How they are related? We have done this for one sample and two samples before. Here we are doing this for one sample. On chapter 23, we're going to do it for two samples. All right? Okay, let's go through the first example and see what we have here. In 2012, the Arkansas Game and Fish Commission gave an employee satisfaction survey. One of the less pleasant findings was that of the 413 employees who responded, 289 either disagreed or strongly disagreed with the claim that employee morale is treated as priority at the agency. The response rate for the survey itself was 73.1%. If all employees had responded, let's assume that the proportion was in fact 68% who disagreed or strongly disagreed with the statement. What is the 68%? Out of the blue, I'm just going to ask you, what is the 68%? Notice that if all employees, when you include all employees, this becomes population. You're taking proportion of that population, which is going to be 68%. Very good, Kelly. Yes, 68%, and that would be P. What are the values of P hat, P, and N for the proportion of employees who disagreed or strongly disagreed with the statement? We're going to calculate those values. So basically, P hat, P, and N are unknown. Okay, so what is the sample size? The sample size is 413. That is the sample size. That is, let's make the difference between the n's here. Now there might be a confusion here. This is the sample size 413. Okay, I'm gonna call this one. Let's make the symbols different. So this is n. We are at. Okay, they call this n. I'm gonna call this one n, capital N, sample size. All right, 413. So number of successes. Number of successes. What is the number of successes? We have out of 413, 289 said disagreed or strongly disagreed. So that would be 289. Okay, so what is the formula here for p hat? P hat, we have number of successes divided by basically sample size. Our sample size is n, not lowercase n. I want to differentiate this n with that n. This is the population n we are looking at, number of employees, basically, overall. So what do we have here? Number of successes is, we calculated 289. Total number of sample size, 413. And if you do this calculation, you come up with something 0.7 or 70%. So 70% success, basic success rate, that means strongly disagreed, or what is it? Strongly disagreed or strongly disagreed. That is the 70% of it, of the sample, for the sample. So we got this P at P, we mentioned that, Kelly mentioned that. Here we have P is, because we are dealing with all employees, that would be my population, and we are taking proportion of that employees, that means P, and P would be 68%. Okay, now if I want to find how many employees are in that agency, right? Or what is it called? Agency? Yeah, I guess. Fish Commission, Arkansas. Yeah. Anyhow, if you want to find a total number of employees there, what do? So you're going to look at if you take what do we have? We should have more numbers here. What do we have here? We have the response rate for survey itself was 73.1%. So 73.1, that means the response rate, that means out of the total population that answered the questions, that means, what was it, 413. Suppose n is, the total employee is n, right? Total number of employees, all employees. Call it lowercase n. Out of these numbers, 413 are picked to answer the question, employees. So that would give you the ratio. This is ratio 413 over the total employee. That would give you 73.1%. Right? So another way I'm saying it, n is equal to, so you have, maybe I should write it differently. That makes sense if I write it this way. Okay, if you have, what do we say? If this is the total, no, let's write this one. This is the sample size, total number of sample that we have, sample size. This is the total number of employees. The ratio of this is 73.1%. This ratio is, that's what it says here, right? If you read this, it says, claim that employees' morale rated this. The response rate for the survey itself was this much. The survey was under 413 and the response rate was 73.1%. So if that is the case, from here, I can calculate lowercase n, right? N would be, this I can rewrite, this one as 0.731. N would be basically I can put 1 here and just exchange these two. That's what, when you have here, I'm going to show you, A over B is equal to C. You can put 1 here, then you can exchange these. So that means you can exchange that with that. This is the same as this. Or this is the same as, you can exchange those two. You can say 1 over, exchange those. B is the same as C over A. All these are the same. So in this case, I'm going to put 1 here. So if I exchange, you can see that if I exchange between those two, I have n equal to, right, n divided by 0.731. N is the sample size, 413 divided by 0.731. If you divide that, you come up with something approximately 564.97. Cannot have a fractional person, so this has to become 565 people. That would be the total number of this agency employees. They work for Arkansas Game and Fish Commission. That is the total number. I guess we calculated everything, right? This is N, we did this. This is P, we did that, and that's P star, P hat. Okay, questions? All right. Now, let's look at some definitions and theorems here again. This is a theorem. You're familiar with this with different notations. This is what I'm saying. If you look at this one as a whole, you can see that, oh, this is a normal curve. This is what we called there in the past, we called it X bar or X, and this is stands for, things like that. You can see the similarity, but at the same time, when you look at the whole thing, because you're dealing with the proportion, you have different kind of different symbols, and that is confusing to some of the students. But if you look at it in terms of conceptual things, you can see that they're similar. Only thing has changed is symbols. The range that it falls in. What is the question? Let me see what the question is here. Gotta go up. Rosie, what if one p-value statistically? Oh, range that it. What's going on? Oh, don't know what. How come that changed? But there's no question. Okay, sorry. So what we have here for large n, we're looking at large n. You're going to see what the definition of n is, large n. But this is, again, this is the sample proportion, right? Remember that? This is sample proportion. This means normal curve. We talked about the normal. This wiggly thing with the dot above it, on top of it, this means approximation, approximately. So remember, we always say approximately normal curve, approximately symmetric. That's what it is. Here, this p-value is population proportion. And this one is basically standard deviation. Standard deviation. This was similar to what we had here. X, we said that it's approximately, if you recall, go back to your old notes, mu and sigma. This was, you're looking at this and you're basically approximating this one based on What you have mu is the population mean, and standard deviation. This was a normal curve, and this was the approximate curve. We had it before. And in the case that this was not known, sigma wasn't known, we put what? We said S over square root of n. S could be S squared, or you can rewrite this one as S squared over n. I mean, all these, you can see similarity here. This goes with that, n goes with that. P, because we are dealing with proportion, replaces mu. And this entire thing, if you can see that I have a p squared here. This is s squared. That's the only difference that you're going to see here. And n is n, square root is square root. Okay, in other words, when the sample size is large, we're looking at the large n. This should be large n. The sample proportion is approximately normal with the mean p. That's a proportion, not the, we're looking at the proportion. And standard deviation, this value that we have. Okay? Now, definition, given a large SRS size n for a large population, a large sample confidence interval for P is given this. This is a condition. We've got to make sure that this happens. Large, and you're going to see the definition of large later. So if this is large sample confidence interval for P, then you can use this formula. Do you see that? Now we have, you can see the similarity here. You have P hat, sample proportion, plus or minus, Z star. Z star is the critical value. And instead of having, we used to have S squared here, now you have P proportion, sample proportion. And 1 minus, this would be success, that would be failure, right? The reason for that, well, maybe it's the next one, we'll talk about it. Okay. So this would be for confidence interval. We use it for confidence interval, this one. So I'm going to show you what we had before for X bar. Remember, we had X bar plus or minus Z star, and we had sigma over square root of n. Again, I can erase this and write entire sigma squared over n. It's the same as that one. Okay? So you can see here we use sample mean, sample proportion, that's Z star, n is n. The only difference instead of putting sigma squared here, now you're using sample proportion and 1 minus sample proportion. So one is called successes, the other one is called failures. If A is in general, if A is successes, B would be 1 minus A, and that would define failures. Because number of successes plus number of failures should be equal to 1. This is like a probability. You're looking at it. If you say you toss a coin, the successes of getting tails is 50%. The failures of not getting tails but getting heads, it's 50%. Yes? If you're tossing a coin and you want to see how many times you get 6, the 6 when you toss a coin, so you say A, the successes for tossing a coin, tossing a die. So number of successes, you want to get it for 6. Number of successes for 6 would be 1 over 6. So therefore, number of failures that you're not getting 6, that means you're getting 1, 2, 3, 4, 5. That would be 5 over 6. B would be 5 over 6, which is failure, number of failures. You can see if you add those two numbers, it always becomes 1. Number of successes, rate of number of successes to the number of failures, if you add them up, it has to become, the probability of those two have to become 1. Okay, let's go back here. Now, this is the definition for this. This estimate here estimates P population. Remember, X bar estimated, this X bar estimates mu. Here, P hat estimates P. This is population. Z star is critical value. Critical value. And this entire thing called, if you remember that, standard error. Same thing here, critical value. Standard error. Okay. Okay. This is standard error. Margin of error is this one. The same thing goes here. When we include Z star with the standard error, it becomes margin of error. Right? So notice that we have here P hat in the margin of error since P is unknown. Because we don't know, because we are estimating P here. So here, instead of putting P, we're going to put P hat here, because P hat is known. Remember, the same thing happened here. If sigma was unknown, what did we do here? If sigma was unknown, we put S squared. S squared was for the single sample, one sample. S squared was standard deviation of a sample. We put this one here, S squared. Here we are doing the same thing. Since we don't know what P is, because we use P, we don't know what P is, we're going to use P hat for both of them. Oh. I'm terribly sorry. I was just looking at here. Let's go explain this one more time. Okay, as I said, this is a critical value. This is a standard error here. Z star is a critical value. Compared to what we have for before, Z star is still critical value. And the square root that we had here, this was standard error. And remember, in one sample when we have there, we use, this is standard deviation for sample. Due to the sample that we had here, this was the size of the sample. It's the same thing happening here. This is the proportion of the sample. This is size of the sample that you have. This is the critical value, the same as this critical value. And this standard value of sample, this standard deviation from sample is similar to what we picked here. Instead of picking, this used to be sigma. If you don't have sigma, then you resort to S part. It used to be sigma squared. And sigma was known. Since we don't know P for our experiment, so we are going to replace P with the P hat, because we know P hat from the sample. And that's the reason these are P hats. Okay. This is here what we have. Notice that we use P hat in the margin of error since P is unknown. That's what we said. We use P hat since P is unknown, the margin of error. Standard error of P hat is, we said that it is this one. We mentioned that, standard error. So SE. Now, this is the definition for large sample confidence interval for P. Remember, we had the large sample confidence interval for P. This is the condition. If the problem is asking you, this is a large sample confidence intervals for P, you have to fulfill this conditions. The conditions are n times P hat must be greater than or equal to 15. I'm going to rewrite it here. N P hat, I'm going to define this. N is basically, this represents number of successes. This has to be greater than 15. Where does this come from? If you look at the first page, you have this formula. Watch. This is the first page. In the first page, you have P hat. So I'm going to write P hat, number of successes. Oh, successes divided by, this is divided by sample size, n. So now if I multiply everything by n, both sides, n cancels with n, therefore you have this. NP hat, therefore you have this, you can see that NP hat is equal to number of successes. Comes from there. You can't see paper? Oh, this was before. Oh, no. Okay. So what we have here, so you see that how we got this one. This is from page 1. All you need to do, multiply both sides by n, then you get this number. And you need to have this NP to be greater than or equal to P. That is first. Second, n minus 1 minus P hat, this must be equal to 15. If this is the number of successes, so if I say, if P was number of successes, 1 minus P hat would be number of failures divided by n. So again, this times that, we get this number. So number of successes, this would represent, let me write it this way maybe. This would be number of failures. This has to be greater than or equal to 15. Minimum, it has to be 15, but greater than 15, that would be great. That is the number of failures. And also the last one is the population is at least 10 times as large as n. So you want to say population size must be equal to 10 times sample size. Actually, at least should be that. It could be greater than that. So if these conditions met in our problem, then we say, okay, we can use this confidence interval formula. Even when you use this confidence interval, it's still not reliable. You're going to see that. Then we are going to resort to another formula. It's called +4 formula. But let's just continue until we get there. So when the number of successes here and the number of failures are both at least 15, we mentioned it here, and the population is big with respect to the sample. This is the condition for large confidence interval. This is over here, both sides. Are there any new functions that we'll need for Excel? I'm gonna look at, I put that Excel last week. I gotta look at them. Don't think so. The next new function, I explained the T's and everything on last lecture, but I will look at it after the lecture to see if you need more stuff. I might just put a page on Canvas in case if you need anything extra. I'll do it either tonight or tomorrow, hopefully tonight. I will look at it, I don't remember, to be honest. I guess not. My assumption is you should be able to do that. The only difference is that we are going to have, well, we're talking about population. Maybe you need something extra. I will look at it. I don't think so. Okay. So we are with this, that's the way we are going to use the confidence interval, provided that these conditions match. If they match, then we say, okay, we're going to use this formula and do our calculation. All right. Let's go and do next page, page 3. So this is example 2. Gallup poll found that 74% of the 2027 smokers they contacted answered yes to the question. All things considered, would you like to give up smoking or not? Find 98% large sample confidence interval for the proportion of US smokers who would like to give up smoking, all things considered. So we got to look at some numbers here and see if these numbers are gonna work. We are gonna look at. We want to see that if we have these 3 conditions met. If it's met, then I can calculate confidence interval. So what do we have here? We have, so we're going to calculate number of successes. Number of successes, we said that it's n times the hat. So what is n? N is the sample size. And what is the sample size? 2027. And the p hat is, what is p hat? P hat is, because it says a Gallup poll found that 74% of the smokers they contacted answered yes. That is the success rate that we have for this question. And that would be success rate. Success rate. And that is 74% or 0.74. So knowing those 2 values, right, I can calculate number of successes is equal to, so I have 2027 times p hat is 0.74. If you calculate that, you get, so I get something around 1500. 1500 is greater than or equal to 15. Check mark. Yes, that's for the first one. Okay. Now I'm going to calculate this for the failure. So for the failure, that would be, so 1 minus p hat, that would be failure rate. That would be equal to 1 minus 0.74, that would be 0.26 or 26%. Okay, so now we are going to find number of, just a second. Okay, well, we'll do this on Monday, next Monday. All right, folks, you have a good afternoon. I will look into that Excel question that you asked. If we have something that I will look into that. If you need more function, I will put them on Canvas. Other than that, I think you should be able to do the Canvas problems and also WebWork problems. Thank you very much. I'll talk to you guys on Monday. I sign off.